So now we start the second session of today, and we're really happy to welcome Zhi-Xun, who will talk about cuprate phase diagram. So finally, we'll figure out what we're talking about the whole weeks.
Okay, great. Thank you very much for the opportunity to show you some of the results I have. Let me start out by thanking the organizers for this opportunity, and also in the funding agency, the Department of Energy, for supporting our research over the years. I also want to acknowledge the KTH and the Swedish Research Council. I've been having a great time here as a visiting professor. So, for this talk, this outline, that's my goal. If this is a very, very active audience, so I'm trying to pace them down. If I can finish these three, basically a recent result and a reflection of the phase diagram, that's mission accomplished. Anything beyond that, if you allow me to continue, then I'll talk a little bit about benchmarking the Hubble model. Is that both necessary and sufficient? Then it's an exciting meeting, so there's many issues discussed about it. So I prepared some slides just for discussions, because yesterday there are many discussions about how to fit and what's the component and all that. So that's, and in case, most likely I won't be able to go through, there's a review article and there's 2 YouTube talk. One is my colloquium here, and one is a little bit earlier result. So that's what okay. Despite all the occasional heated discussions in this room, this group is capable of being happy. As you can see, when we have food, we all seem to be really happy and have a very civilized conversation, you know. Now let me also showing, you know, by starting out with a quiz. Just for entertainment, I got it from my student. What is this curve? If you guess it right, you earn your right to interrupt at any point. Well, number of papers, because they give the hint. That's right. You got it right. Okay. Now, let me contrast that to another curve called Hyperloop for emerging technologies. There are usually 5 phases: starting, innovation trigger, and then peak of inflated expectation. Okay, you can see your favorite technology here for our field. Quantum computing is right on the rise. You probably see it go all the way probably. Then there's phase of 12 of disillusion. Okay, then there's a slope of enlightenment and a plateau of productivity. So where we are in the cuprate problem. Well, now you can see the similarity. You know, that's this peak, then that's sort of the trough here. And we are, you know, this error, depending on who your favorite topic, we're really into this enlightenment of that. That's the percentage of papers in condensed matter which are high TC related. So anyway, that's the end of the entertainment part of the presentation. So this sort of give you a sense of the cuprate problem. In a sense that this is the phase diagram, and we are still trying to sort out. There are many versions. I will try to talk about the latest somewhere. In an idealized way, then the single layer is the system. We look at it. Okay. Yes. By which it's not symmetric. Yes, it is not between P and N. Correct. It's a symmetric in spirit, the similar phase, but quantitatively they are not. Yeah, okay. So let me say a few words how the experiment's done. It's a photoelectric effect, and you have photon and you eject electrons. Okay, you analyze the energy and the momentum of the electrons. In many ways, the advance of technique is that simultaneously you do spectroscopy and imaging. What I mean by that is, as the electrons travel from sample to your spectrometer, the energy filtering is done by, it's a hemisphere, two pieces. You put a positive voltage in the middle and a negative voltage outside. So the electron will bang, okay? Only the electrons with right amount of energy will go through and being detected. Okay, otherwise you hit the wall somewhere. So it's an energy filter. Also, the hemisphere is a extremely good imaging device. Okay, that means that anything you detect at the detector, you can trace back where the electron entered. That means you know the direction electron enter your spectrometer. So you know the energy, then you of course know the momentum of the electron. And also you know the direction. That means you know the vector momentum electron. So it's the electrons in free space, but how you translate into that, into a real material, you're using conservation laws of energy and momentum. And in this case, the fact we are often dealing with two-dimensional materials because the momentum conservation in the CXs not guaranteed. So in 2D material, this technique is particularly suitable. Another thing is also interesting from the point of view of comparing to theory is the fact that it's measured spectral function. So one of the, one of the relatively simple things you can calculate, and so that comparison with microscopics makes it easy. So that's the picture. Okay, now as a many-body spectroscopy, there are a few things you can do about it. So in a free electron, you have a very well-defined energy momentum relationship. Okay, if you would have, let's say, a collective mode, and in this case, let's say you have an electron coupled to a phonon, you should see a break in the energy momentum relationship at the frequency of the phonon. Okay, so that will be one way. Now, if you have an electron-electron interaction, a lot of the interest in this topic will be, then you sort of see a slope change and width change. Okay, of course, you can also have spin orbit, and in the surface, when the inversion symmetry is breaking, then this two spin orbit component being separated, you can also detect that. So those are the things you can learn. Of course, those are microscopic interactions, then they lead to interesting phenomena that including superconductors. Okay, then you open a superconducting gap, or charge density waves, then you open a CDW gap, or there's modern physics, so on and so forth. Okay, there are several reasons photoemission sort of become a very efficient way to measure, to study quantum material. One of the many is the fact that in the relevant photon energy range, the photoelectric effects, the quantum efficiency of photon in, electron out is very, very high. Okay, so naturally you have a very high efficiency. Second thing is it's a charged particle. That means that unlike photon, you really can just manipulate the energy without contacting electrons, that you just add electrical field. So that makes it very efficient. Of course, we all know as a scientist, in the end, it's really a combination of the ecosystem. You really need a scientific agenda, like discussions in this community, you need materials, and you need measurement. And of course, there's a lot of computing too. Okay, so let me acknowledge my collaborators. What I'm going to talk about are the results by Zhi-Xun, He, and started with earlier work by Innovation. And our research really is enabled by the two individuals, Donghui Liu, who really built this workhorse spectrometer, which is later on joined by Makoto Hashimoto. And we have really the fortune to work with many sample growers. But for what I'm going to talk about today, mostly come from Hiroshi Aisaki. That's more than 2 decades collaboration. On theory front, I mean, it's a very stimulating environment with Steve and Tom's group there. And also we benefit a lot working with Donghai Li and early days in Naoto Nakaosa, then a lot of wonderful visitors, including, occasional excitement from Yang Zanen and also wisdom from Doug Scarpino. Okay, so for those of you who have not seen the instrument, that's like a picture. You see a lot of steels, and that's how you get a UHV, ultra high vacuum. For the type of measurement of the sensitivity, you need extremely low vacuum. You need about 10 to the minus 11. So it's that's basically 13, 14 order of magnitude from the air we're breathing in terms of vacuum. And that's the typical setup. And I want to also acknowledge the contribution by Rob Moore in building the material synthesis capabilities which we use. Okay, again, samples from Aisaki. And again, this is the phase diagram. For this talk, I'm going to focusing on a segment of the phase diagram, which is there's a critical point here. That means for simplicity, I'm going to mostly focus on in the overdoped regime. Means that is already on the side, TC is going down. Okay, so that's the optimum doping is about 15%. So just give you a reminder about in this phase diagram, there's this eminent phase called the pseudo gap. Okay, to give you a reminder about what is the pseudo gap. Well, in metal, we have something called a Fermi surface. It's a concept of area. And if you take the area enclosed by the Fermi surface to give you number of fermions in the system. Unless you have special circumstances, you should not stop in the middle of nowhere, okay, because it's a concept of area. Phenomenologically, often you see only one segment in the experiment, okay. One way to think about is, in fact, the Fermi surface is like that, and somehow for whatever reasons it's being gapped. And because it is not quite known how this is being gapped, so it ended up with the name. Anytime you think about a pseudo or strange, you know it's a subject to debate. Okay, that's why it's sort of called a pseudo gap. Just give a phenomenology that's fairly generic. There's 3 families of compounds, and you can see them. You can see these the Fermi arms. So it's sort of the Fermi surface stop in the middle of nowhere. Okay, that's the generic phenomenology. Now let's look at the temperature dependence. So here I'm showing you just an illustration, a set of data taking at the anti-node where the gap is the largest, okay? And as you can see in this case, if you will measure as a function of temperature, at a low temperature, you see a superconducting gap. The spectrum is being symmetralized, but for this purpose, it's okay. And as you increase the temperature, you can see the gap persisted up to superconducting transition temperature. certainly doesn't close, and then sort of close at temperature substantially higher than the superconducting transition temperature. Okay, so this gap in the normal state is the phenomenology of the pseudo gap in one sense. Okay. There's another aspect of the pseudo gap is that if you really look at the spectra and taking at the antinode, that's the superconducting gap, measure the lowest the temperature, then of course the gap is a measure of the superconducting pairing strengths. Okay. Now, as you go under doped regime, the superconducting transition temperature goes down, as you can see here. But you can see the magnitude of the gap gets bigger. Okay. There's another phenomenon you already can see. On the other hand, the coherence peak gets smaller. Okay, as you go under dome. So these are the sort of phenomenology. And from the early days, most people will say this superconducting gap, right? And it's because it sort of goes through the superconducting transition temperature without any sort of strange change of that. So it's saying that it'll be pairing in the normal state. That remains to be true, but as you study the system, it becomes richer. I'm going to just say a few words as a reminder about this thing also, peculiar phenomenon. So it's now the reviewed a richer picture. Okay, one of the things, this actually is 20 years ago, there's this basic phenomenology that you can see that's the single particle spectral way of the coherence peak, and we call it the quasi-particle spectral way. You find that in this underdoped regime, there is a slope. So just a reminder, there is something peculiar about this system because it shouldn't be. And in a naively, that's called this single sort of coherent peak intensity. It scales with the specific heat and mu-SR in this way. So these are all just background information about this mystery about the pseudo gap phenomenology. Okay, now for the last 15 years, we begin try to make better sense of a bigger picture of this phenomenology of the electronic phase diagram. So started by looking at the doping dependence, temperature dependence, and the symmetry property. Then around 10 years ago, during the thesis work of Inovishik, we begin to zoom in this regime, which there's a critical point. And that's a lot of interest of this conference. So that's what I'm going to focus on. Okay. So we find various interesting phenomena. That's the things I'm going to talk about. In particular, I'm going to talk about these 3 recent papers. And in particular, this paper about sort of a phase diagram in this way. Okay. Okay. Again, this is the phase diagram, and what I'm going to talk about, just for simplicity, is focusing on this doping range, which includes this ostensible critical doping at about 19%. Okay. Here is the work about Inovishik's thesis work. She measured the D wave node. Okay. And here's the slope of the D wave node. And she measured that for underdoped 40 Kelvin, 55, that's superconducting transition temperature. As you can see that as you go increase the superconducting transition temperature from 40 Kelvin to 92 Kelvin, more than a factor of 2. The slope, which is the most sensitive measure of the D-wave superconductivity, doesn't change at all. Okay, so that's the pairing, doesn't change. On the other hand, so that's telling you superconductivity in terms of TC is controlled by something else. But somewhere around this doping, 19%, suddenly it scales with TC. Okay. So that's the peculiar thing about this set of data. There are a lot of work she did, including the picture you've seen by Arcadia earlier this week of the work, which we can go into it later. So now I'm going to summarize, then I'll show individual results. We sort of think the phase diagram is more like, at least for this material system, it will look like this. Okay, near the critical doping, there appear to be a fairly steep boundary, and to the left, to the right, looks quite different. Okay, there are phenomena happen at a very high energy. Okay, and I'll talk about that. Then, depending on this side, depending on which quantity you're plotting, you could have different sort of slopes, but it's all sort of bounded within this range. Okay, so that's this. I'm going to talk about this sort of vertical type, almost vertical type of boundary is interesting, almost like two faces. Okay, now let me show you this aspect of the data. Okay, the more recent work was done with more stringent experimental criteria. I talk about the importance of vacuum. One of the things only the sort of the aficionados of the technical one knows that, because you are working on experiment on the surface, okay, and you have gases, even though you're in a very high vacuum, you have gases, and when you measure at a low temperature, the gas can condense. Okay, if you do a temperature cycle, it's extremely important that the gas in and out of the surface being controlled. Otherwise, what happens is you will have molecules condensing on your surface, either O2 or CO, and they can take electrons away or adding electrons. So your doping may change. Therefore, usually you wanted to do the experiment. You know, there are certain features that are less sensitive and certain features more sensitive. You want to do the features in experiment with a very controlled, extremely local heating. Therefore, you can have everything to be rather repeatable. This is really a very important technical contribution by Hashimoto made this possible. Okay, now here, this will be the meat of this data and presentation. So in a relatively narrow range, I'm going to focus on it's from 16% to about 21%, so 5% doping range. Here's the 19% where the earlier work shows a slope change in the superconducting gap. Now I'm going to show you the spectra taking to the left of the 19%. Okay, so this 16%, this is the data taking at 18.5%. Okay, photoemission measured occupied state. However, if you do measurements at an elevated temperature, you can see states above the Fermi level because they are thermally populated. Okay, and the thermal Fermi-Dirac function is a very simple function. You can just divide it out. So that's the reason you see intensity above the Fermi level. Okay, you can see that as you cool down for this part of the spectrum, at high temperature, nothing happens at zero energy. As you go to lower and lower energy, you see a suppression of denser states and energy. And with this energy scale, it's pretty high. Okay, so that's the generic, but it's a totally featureless type of behavior. In contrast, if you go to the right-hand side of this boundary, okay, you see a clearly defined peak at the chemical potential, okay? And you don't see any suppression of denser states at zero energy, okay? So all these appear to be one class, and these appear to be another class, okay? So that's qualitatively different type of thing. And this suppression happens certainly at temperature 200 Kelvin or even higher, okay? You can see on this side. So that's the difference of it. Now, if you further cool down this guy to even lower temperature, just look at him. If at this temperature, you can see the single peak begin to develop into second two, and eventually split into two and developing into the superconducting peak. Okay, so this is a behavior you would expect it at the Bogoliubov quasi-particle. I have a peak spectral intensity at a chemical potential and develop into a Bogoliubov quasi-particle with a spectral weight UK square and VK square. Okay, now everything looks like a sort of what you would expect, except whatever this happened at a temperature much higher than the superconducting transition temperature. Okay, later I will show that data in this range, in this doping range, but is above the superconducting transition temperature in the normal state. You'll see that this one has a particle-hole symmetry, as you would have expected in a superconductor. Now, on this side, you can see as I go to lower and lower energy, you begin to see develop an edge, and this edge eventually develop into a quasi-particle peak. Okay. Several things worth noting. At a big scale, you find that, in fact, if you really look at the low temperature, the difference is more subtle. There are differences, okay? The more dramatic difference reveals itself at higher temperature in the normal state, okay? Also, to the point of Nigel Hussey's talk earlier this week, you see that this feature, okay, and what looks like a peak we'll call the quasi-particle, but it's pretty, you know, it's after the chemical potential is still pretty broad. Okay. Yeah, still.
Looking at the lowest temperatures,
yeah,
it actually looks to me like there's still a big difference, but I don't know if it's meaningful. That on the low dope side, the spectrum seems to have a very broad tail. It's not visibly decreasing as you raise the energy, whereas on the overdoped side, it's distinctly dropping with energy.
Correct. Actually, I will show a more refined, amplified data comparing at the low temperature later. Yeah, it is correct. But on the other hand, when you look at the a gross picture, the bigger difference is more easier to visualize at higher temperature.
I don't know. I mean, I think if I blocked out the low energy piece where more's evolving, it seems to me you see this difference at low temperature.
Okay. Yeah. So that's there's many things about it. Also, I will just to emphasize what Steve has said earlier. Language also means that there's broadness at high temperature on this side. Okay, there's nothing you can talk about the quasi-particle. It's not due to trivial disorder of material. They can also give you a very broad featureless thing. But of course, a trivial disorder will not suddenly become something really well-defined quasi-particle. Okay, so let me say a few words about the to dig into a little bit more, then there are two sort of energy scales. Just look at here. If you really look at the higher energy, then there's this broad feature at about 100 to 200 millivolt in this range. Okay, one way to visualize that would be if you really look at the high temperature, make a difference curve between the spectra taking 150 and let's say 250, you find that there's a spectral wave transfer from near the Fermi level to a very broad and high energy scale. Okay, so that's the difference curve of these two spectra. On the other,
This is a perpendicular to Fermi surface at the antinodal point.
this is a cut across the antinodal point. Yeah. Okay, and each of those are just spectra, and this is one of the spectra. Okay, and make a two different temperature cut. On the other hand, if you look at the difference between at the lower energy, slightly above TC and a 90 Kelvin, you find that the deficit, the changes most happen in the regime near the Fermi level, near the regime of a superconducting gap. Okay, and this kind of high energy spectral wave transfer is not there in the overdoped regime. As I said, this guy does not open up any gap. It just sort of develop the single peak split into two. And you can see it in a similar way as you go to lower temperature. This, even in the normal state, you see a deficiency of the spectral wave here. And that is the superconducting gap. I'm going to now amplify. So if you will say this being a superconducting gap, let me just say that a comparison between a superconducting activity and, let's say, just for example, a CDW, then you can see that in this case, in a superconducting gap, it happens at KF. If we make a cut of data in momentum space, then you have a situation like this. Or if you have a CDW, then this point may or may not be, where the gap shows a minimum, may or may not be coincide with the KF, but for superconductivity. So that is something you can go and try to test if you see a gap. Let me just say that for example, in one of the single layer systems, and in the pseudo gap regime, you can clearly see that where the gap reaches minimum, indeed deviates from where KF is. Okay. Now, what about those overdoped regime? In this here, I show you data cuts in this entire range. And as you can see, data taking with a sample here are above TC and here below TC. You can see that. Now you can plot the spectral intensity both above and below TC, but for our purpose, we want to show that in the normal state is also has a particle Hall symmetry. And indeed, if you plot a different regime, and you can plot the energy position of the upper and the lower Bogoliubov quasi-particle branches, indeed, they look like symmetric with respect to zero in this. So now let me say one more thing about this. So this will be something like a phase diagram, and we plot those temperatures where we can see the low energy gap, and that is where the pairing happened already. Of course, there's higher energy physics in this, and this will be the thing. If you really look at this, you find that I had hoped to show you a case that crossing this boundary, okay, the single particle shows a dramatic change. But you find that the temperature at which the pairing happened doesn't know this very much of this. Okay, so I mean it's crossover temperature, so it's very hard to define. But there's no sudden change in this. So let's dig this into a little bit more. Okay, so what happened? Now, still come back to your point here. If I will plot the peak position to the left, I'm sorry, to the left and to the right. Okay, now if you amplify that, then you can see they to the left belong to one group, to the right belong to one group. And you can see indeed the energy position of this peak, which reflects the pairing, shows a pretty large change, from certainly more than a factor of 2 in terms of pairing strength crossing. This is also consistent with the sister's work of He earlier. As I go from overdoped region in this very narrow doping range, okay, you can see that the superconducting gap position, as shown in this red, goes somewhere from about 10 millivolt, okay, which give you a 2 delta over KTC of 4.3. It's the sort of value of a weak coupling DCS to a factor of 4 higher in this narrow doping range. Okay, I'm just saying, go in passing, there's also this feature, okay, for those of you who are familiar with tunneling results, these are often associated with mole coupling, also shows a similar type of change. The third plot, which when I talk about phase fluctuation, is also a quantity, is the intensity of the spectra at the 0 frequency above TC, also show a change of that. So this then should we take this data and go a little bit further, and it's so now with a more stringent, again, if you plot just the superconducting gap, okay, across this, okay, that shows this behavior. Again, you can see almost a factor of 4 change of that, okay. And if you plot this quantity, again, divide by TC, it also shows this behavior, okay. So that's consistent. However, if you would plot this guy, okay, instead of divide by TC, if you divide by the fluctuation temperature, then you can see, intriguingly, the change really happens instead of sort of gradually here. Maybe there's something more sharper change in this. So that is interesting to say that as you have the phase diagram look like this. Okay. So now let me say one more thing about the related also point to the 20% being special about it, is now you say there are 2 gaps. What about the relationship of that? So here is sort of, if the 2 gaps were simple and one adds on top of another, it's like adding in quadrature. At T star, you opened up one gap. At TC, you opened up another gap. Then the 2 gaps add in quadrature in naively in this way, in other words, adds on top of each other. Then if you would plot the spectral intensity, okay, spectral intensity, then you ended up in this way. Okay, so again, if you use segment the spectrum with different temperature windows, then if you look at the low energy for now, you would expect the following. If you look at the spectral weight in this kind of window, at the T star, when the pseudo gap happens, you should see the spectral weight decreases. At TC, it just decreases even more. Okay, so that's what you would have expected if they were. In the data, if I also plot the low energy one, okay, then you can see that at the T star, indeed, the spectral decreases, okay? But at TC, instead of decreasing even more, actually increases. That means that superconductivity actually countered some of the spectral weight loss by the pseudo gap. And again, that's sort of the naive expectation of it, okay? So if you take that, then you can say that probably means that these two states are counter to each other. Okay, so if I will now naively take what is being observed in similar systems of charge order intensity, as the charge order peak develops at TC, okay, that peak also decreases. With that as an input, then you can sort of simulate. But this is the one way to think about. So now if I would, instead of only looking at low energy, I will look at all energies. Then you can see again, at the low energy, you can see a T star, you can see low energy spectral weight decreases. Correspondingly, you see high energy spectral weight increases. That's the high energy. So there's a transfer from one to another. Okay. Then at TC, the low energy spectral weight got repaired some, and you can see the increase of a high energy spectral weight at least stops, okay, in this way. But if you want to use this jump at TC as a measure of the sort of the antagonizing relationship between these two, then you can see as a function of doping, okay, as a function of doping, this ends somewhere around 20% also. So this is also consistent with the fact that there is some physics change in this doping range. Okay, so now let me sort of again summarize this, or to say that hope to show you data shows a result seem to suggest that there is a boundary not exactly vertical, but almost vertical type of boundary. And to the left-hand side, many things happened. And to the right-hand side, it looks like sort of looks more normal, other than also very strong superconducting phase fluctuation in this way. And I will note also that if you rigorously try to argue for the Landau Fermi liquid, then the peak, even in this region, is broader than you would have the energy. Okay, so that's, now let me make a connection to this diplomatic phase diagram, at least mentioned in this meeting by 2 of the 4 or 5 authors. Many things happened in this way. So this will be our view of that. There's no contradiction in that. It really depends on which physical quantity is. What it is plotted here, this was also shown by Nigel, is the spectral intensity at the Fermi level. And you can see in this way. So this tilted a little bit in this range. So one will say that there seems to be a boundary in spirit in this material, and many of the things happened here will be happen on this side of the phase boundary. Okay, so that's okay. Now that's sort of result. Now let me say a few words about the phase fluctuation in this problem. Okay, so I mentioned that here already there's a gap at the gap in this range looks, even in the overdoped regime, on the right-hand side of this vertical boundary, it looks like particle hole symmetric. Okay, then the question will be, what is the spectroscopic signature for the global phase coherence? Okay, this is sort of a fluctuating superconductivity is a fairly generic phenomenon in low-dimensional system with strong disorder or low kinetic energy. You can see various kind of materials. Okay. However, if you really look at the bulk material, okay, you can see materials where the conductivity or resistivity changed by 4 decades. But when you plot T pair over TC, sort of hug around 1. Okay, and the cuprate is distinguish itself with a bigger number, and the family we studied, bismuth 2212, is in this range as a bulk material. Okay. So at least within the BCS regime, we have zero resistance, we have the Meissner effect, we have the specific heat anomaly, then which is associated with the order parameter gap delta, which sets in at TC. Okay. Now, all this, of course, seen right at 96, and this also seen by John, Roland, and Jeff Talon for a long time ago. So the question will be, what will be, now we already know, we already use the gap at another temperature, so we can now use that same thing, will be the thing which is corresponding in the spectroscopy, corresponding to the specific heat jump. Okay, so this is what Shudi set it out to do, again, with a very well controlled. I'm going to later on show, instead of usual formula, dense of states multiply, f log f plus 1 minus f log 1 minus f. Okay, and he said, I'm going to use naively plot the spectral intensity at the chemical potential and see what happens. So he's going to just use this quantity of spectral intensity at the Kf and try to calculate this entropy type of behavior. And once you have this curve, then you can do a derivative. And that is the solid black curve here is what you get from thermodynamics, basically specific heat measurement. The points here is the spectroscopy data. Okay, so instead of the order parameter delta open at TC, now this global superconductivity encode itself in the denser state, in the spectral weight at the Fermi level. Of course, once you have that, then you can also use the power of the momentum dependence of spectroscopy to measure as a function of angle. And indeed, as you go to closer to the node, you see more filling in of the states. Okay. Let me just emphasize again, what is plotted here is the spectral intensity at the Fermi level for visualization. Here he's plotting the a few spectra in this way, and that is the quantity A0 being plotted here. And you can see that here is the gap happens, okay, and here is A0, and the global superconductivity shows a singularity in the quantity of A0. Okay, and this, by the way, is very consistent with the state being filled in because of the phase coherence. Okay, and also the quantity, how much of the residual density of states at the Fermi level, which is about in the order of 5%. Okay, probably give you a measure of how much disorder in this system. Okay, so I'm going to stop here and say that that's sort of my main topic of the reflection of that of this, and I'll be happy to take questions. And if there's still interest and time, then I can talk about second topic of trying to benchmark the Hubbard model. Okay, so or we can go straight into earlier debates on the various data being discussed. Okay. Yeah.
So you've probably seen a similar kind of notion of a vertical boundary in the Lonzerich-Sebastian data. And in their data, one component doesn't seem to change. The linear resistivity is completely smooth, but aspects of the Hall or the Hall angle seem to change suddenly.
Yes.
Can you see a similar division into parts that change smoothly and parts that change suddenly in your spectroscopy?
Yes, thank you. For those of you who are not familiar, there's work in a different material system, but in spirit is similar, the YBCO by the Cambridge group, and show a very temperature independent, a sudden change at this doping that's being referred to. And Pierce was talking about some quantities seem to go smoothly, some go sudden change of that. And in my earlier discussion, we also find intriguing, if you really look at the fluctuating temperature, T fluctuation, okay, seems to doesn't know this boundary. On the other hand, if you use the quantity of pairing strengths, the magnetic, true, but in our particular experiment, I'll be double counting because I'm using TC to calibrate doping. So that's why it doesn't show a singular, but I will be double using that quantity. Yeah. Okay. So some quantities seem to be smooth, but some quantity does show sudden change. And I show that if I will plot 2 delta over P fluctuation, again, that's a sort of a crossover temperature is hard to define. Okay, but to the zeroth order, you do see a sudden change. So in that sense, it's a similar type of thing, depending on which quantity you will melt. And this in a spirit of
Over TC, I see.
yeah, let me go back to it, and you probably can see. No. This delta, okay, the large change, okay. But if you plot delta over TC, also has a large change, but doesn't seem to have that. But if you plot delta over T fluctuation, you begin to see some change. But it's all these are still work in the sense of there's still a lot of scattering, mainly because you don't have enough. However, it's very different from a quantity which doesn't seem to show much change at all. Okay, so I try to finesse that. How do I find the T fluctuation in the spectroscopy? Either I see the temperature where the single particle peak now begin to split into 2, and I interpret that as going into the Bogoliubov quadrat particle, or in underdoped region, a clearly identifiable shoulder developed, which eventually evolved. And of course, it's a crossover temperature. It's kind of hard to define. So, yeah. Okay, there.
Sorry. So just to make sure I understand, so all these plots are defined by the behavior at TC or at most factor of 2 of TC, T fluctuation. Yeah.
Yes,
You're not going-
50%. As you can see
Yes.
in the order. Yes.
So this behavior, in principle, doesn't know anything about what happens at 5 times TC or
Correct.
10. Okay.
Yes, we try to say there are 2 scales in the problem. Yes. Okay.
You say there how the should gap before the point 90 and after 90 they have dispelled the should gap. And our question is why it is the point 90 and what happened at the 90 the point 90 of this point? Why
think-
it is why not is the another point? Why is it when it is
I understand the way. I don't think 0.19 or 0.21 or these are critical. The more important is not that quantitative that is more important that in many family of the compounds, there is a particular doping. And this doping seem to be a termination point of an interesting manifold physics. Quantitatively, the 19 or 20 or even 17 probably is less critical.
You know, I this is a comment,
Yeah.
just it was triggered
Yep.
by your old data. It's not actually true in BCS theory that the peak in the dispersion is precisely at K Fermi.
Okay.
If you take BCS theory full, so still all mean field theory, but if you go to strong coupling, there is a shift of the chemical potential that's of order delta squared.
Mhm.
So the spectrum will remain particle hole symmetric,
Yeah.
but actually the apparent position of the Fermi surface will shift even within BCS theory, just order delta squared.
True.
That's not true.
Yeah.
So you'll have in BCS theory, what will appear is epsilon of K minus mu. And since mu is renormalized, the system will have its peak at what would be K Fermi at a slightly different mu.
Thank you for the comments, Steve.
I mean, I don't know. I'm not
I
saying it's
don't-
relevant. It's just
My sense is that the gap is small and the misalignment is sufficiently big. My sense is probably not going to change the picture, but that's a good point. Yeah, definitely.
that's a quantitative.
Yeah.
Must
Violation. Well, no, there isn't Lettinger's theorem because you don't have a Fermi surface. You're in the superconducting state. But if you naively interpreted that as a Fermi surface, it would be a violation. This is all in PCS theory. There's nothing, subtle or complicated about this.
I'd like to ask
Yeah.
another question, maybe about your spectral curves when you discuss the competition between orders. Can you show this? So there are 2 peaks, but in between these peaks there is a depression which you mark with red with gray triangle.
Yeah.
Should I think about this depression as also a feature of the spectrum, or do you think it is just?
We at least within a naive model, this suppression is a result of coupling to a phonon system, collective mode coupling of that. I don't have time to develop that, but it's, when you look at the classical tunneling spectra, you see those wiggles. That is, that's how we, okay.
I was just wondering, because from this picture, it looks like this depression is coming closer to this sharp peak, and eventually they eat each other. So this is something which we actually saw in holography some time ago, precisely the same effect. So
let me put it this way.
So if I understand you correctly, you're not relating this depression to any like fermionic physics.
No,
So this is
no.
because of interaction
Yeah,
with photons.
with a boson in the system. Yeah. Okay. Should I, Alex? Should I try to spend maybe 10 minutes, 15 minutes to talk about this? Oh, okay. Oh, okay. Of course, since 1987, articulated by Phil, that the cuprate physics is clearly embedded in the Hubble model. There's a lot of debate on that, and the question we try to all of us will be saying that the Hubble model clearly is necessary, or something like the Hubble model, because they're long at the antiferromagnetic phase, the mod phase. The question is that, is that sufficient? Okay, so that's a progress we made. It's really the progress made by material synthesis as done by Zhi-Xun, and also theoretical calculation by Tom's group, in particular Yao Wang. He has now moved to be on the faculty himself. So let me talk about that. Okay. As articulated in Phil's paper, 87, right after high TC, maybe the physics of the cuprates is in the Hubble model. And for this community, of course, you're very familiar. One of the emerging property of the Hubble model is the exchange interaction, which is self-generated because of the Coulomb U. And that next neighbor exchange attractive interaction could be a source of pairing. So that's sort of the conjecture of that, okay? So, of course, that's very interesting. There's a lot of work, and for this community, you don't need me to tell you that it looks simple, but not easy model to work on it. Okay, so so is this sort of, it's still elusive of that. To the heart of that is the two-dimensional calculation is hard to control. And as a result, when you have a disagreement between experiment and theory, you cannot say it's the model problem or it's the calculation of the model problem. And 1D, we know, I think there's more consensus that the solution will be. So that's what we had hoped to do. We tried to work on the 1D problem for a long time. And in early days, we did study the 1D system, but with the insulating compound. That's the only single crystal was available. And for this community, of course, the 1D physics of spin charge separation is well known. And indeed, this is seeing, you can see that the otherwise a single band now being split into two sort of edges or branches, and with a continuum between them. And quantitatively, you can fit the data with the T being coming from the band structure calculation, with the J coming from neutron scattering. So this has been sort of, there's a lot of work for about a decade trying to get to this point of that. And that's Chang-Yan Kim, and who started this, then he later on worked with BJ Kim after he went back to Korea to get this. So this, of course, is something this community is very well aware of that. Okay. The question is the 1D now, if you see whether you can take the step further, and it turns out it's difficult. Until recently, using a different method, you can grow single crystal films. Therefore, you can dope it. In a insulating 1D, you can assess things like spin, the charge, but you cannot access the interaction between two doped carriers. Remember, photoemission process you're taking one electron out, you're injecting one hole. You're studying the spectral function of the dynamics of the one hole in that. Okay. But you need more than one hole to study excess of that. So here will be the 1D solution of the doped system. Like earlier, the red and blue are the spin-on and hold-on branches. But actually, the solution of the system had many more. But according to the work by Tom's group with the cluster sort of perturbation theory on that, the feature with the strongest intensity is something happened at KF. So this will be folding back. You can think about for metal physics, this will be the KF effect, and this will be 3KF effect. Okay, so this will be something we try to get to it. The technical challenges mostly had to do with difficulty of doping, and you need a lot of effort being made, but in single polycrystalline, so we cannot do formation on them, and the cross section and also the 1D sample is very sensitive. So this progress really is made. Now you can have in situ growth allow you, and then of course coupled to the spectroscopy. Okay. So here we now can able to dope the system from 9% to 40%. Okay, and that is the compound is basically 2, 1, and oxygen 3 plus delta. It's the 1D chain compound. Okay, so what you see here is a sample which is nominally 9% doped, and you see the Fermi surface is 2 straight lines. Okay, and remember this is the 2-dimensional system. When you grow films, you end up with 2 domains. So what you should interpret this is this 2 vertical set is 1 domain with Fermi surface looks 2 straight line, and these 2 horizontal one is another set. And that is one nice thing about you can do momentum dependent study. If you are making a measurement, for example, here, then you are insensitive to the signals from the other domain because that is the regime. The other domain doesn't have signal in this kind. Okay, so that's what we see. Again, we were looking for the KF feature, folded feature, and that's, again, let me just show you the doping dependence. You can see a 9%, 14%, 28%. The key is that as you increase the doping, the distance between these 2 lines gets shorter because you change the doping. Okay, that's the 1-dimensional, but they remain pretty great, like 1-dimensional like band structure. Okay, now this will be a more quantitative instead of imaging plot. I hope you can see, look at the 9%, 14%. You see that at 9%, you can see if I will plot this one, you see another branch coming back down at the KF, and that's the data. Okay, and that corresponding to this feature. And 14%, you can still quite visible, but by the time of 33%, you don't see that thing anymore. So it's also strong doping dependence. Okay, again, come back to, we were looking for this KF feature and this 3KF. Okay, and the data also shows all the things of the spin-on and hold-on, but that's not the focus of it. So now if you compare with the comparison with the Hubble model calculation, then you can see that's what will be the one. The 2KF feature is here in momentum space. Okay, actually, if you look carefully, the Hubble model also have one signal, but it's very weak. Yes, 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 please.
Question
Yeah.
from an outsider. What's a spin-on and what is a hold-on?
Oh, I see. I saw the theory guys would know everything about in one dimension, right? You no longer have a particle in the sense of you have a charge and a spin half type of object. You have everything as a collective type of thing. And one way to visualize that will be if you have a antiferromagnetic chains, and you take one real electron out, you root one defects, okay? And as I move the defects, you will find I end up with two topological defects. One will be the spin misalignment. Okay, maybe I can go back to this just to visualize that. Okay, let's say if I have a antiferromagnetic chain, okay, and I take one electron out, this real electron with both spin and charge out. Now you can see that as this hole moves to here and move to here, you can see it move to here, then essentially you move one spin. But if you move one more, you move to another spin. Now you can see that even though I take only one hole, I end up with two defects. In this case, I have a defect. You can see on both sides, the spin is correctly aligned antiferromagnetically. Now, if I further move this hole, I don't need to do anything on the spin. I don't pay that cost energy. On the other hand, here, I also have a defect. You can see the spin now is misaligned. And moving this guy just by flipping a spin. So the speed of this defect will be controlled by the spin flipping. The speed of this guy will be controlled by as if there's no metabolic interaction. So you ended up with that. From the spectral function point of view, then you have a continuum of excitation. This is a sort of a cartoon.
Okay,
yeah.
Thank you.
Okay. Okay, so that's the comparison. So it looks like the data show a feature which is much stronger than the Hubble model we gave. So we then say, okay, this is the on-site cooling interaction being taken into account. Then to supplement that, you want to add one more term to it. And that's where y'all and Tom's group did the calculation. And in this case, of course, you can add a next neighbor interaction, which is of density form, okay? Now, if you make that term to be positive, nothing really happened. However, if you make that term negative, okay, then you can see that with a value about negative t, then these two seem to agree with the experiment, okay? So there is an additional term of order of t. And one, again, now you can look at the doping dependence because that's another knob. And if you really look at this feature, you can see a low doping, they're very prominent, but it's sort of disappeared around 28% doping. And this calculation also captures that doping dependence just with one extra term too. So there is, this data seems to suggest that the material has a term in the problem, which is attractive interaction, which is much bigger than what is being self-generated in the Hubble model emergent. You can see here, this is the baseline where you kill every attractive interaction. And actually the Hubble model does have a attractive interaction. This is above this baseline. Okay, so that's coming from the emerging exchange interaction. But the experiment has this value to be substantially larger on that. Okay, so that's try to benchmark on this. And with this additional one, certainly on the spectroscopy, seem to be able to have a holistic of both the spin excitation, charge excitation, also the interaction, as well as the doping dependence. Okay, and the hope was because of the similarity of the quantum chemistry, some of the things you learn from 1D in terms of model parameter can be carried over to 2D. Let me just say this, even though the attractive interaction is T, which is substantially smaller than Coulomb U, okay, the on-site Coulomb U. But if you're not competing with the on-site U for the next neighbor, then T is no longer a small number, okay, because that will be the emerging property of J. And let me just say that Tom's group now has also 2 papers published, and that's really the serious work they did. The first one is try to see what happens if instead of on-site electron-phonon interaction as in the hosting model, okay, this red in hosting, instead you use the next neighbor attractive interaction, you find for electron-phonon coupling, you find that actually becomes quite effective. You only need 2 neighbors, then it sort of saturates. And the G, by fitting optics or Raman, is correct number somewhere around 200. So with a realistic parameter, it seems to be consistent with you have a attractive interaction in this range. Okay, and they just also posted a paper on the archive, I think not long ago, maybe, I don't know, it's very, very recent, maybe a week ago or something, to show that by adding this term, actually, you could, certainly with the 4-letter model, I think both CDW and the superconductivity is sort of have exponential role, but the CDW should be more dominating. But by adding this term, I think it has turned the balance around and becomes a more favorable superconductivity. So that's what I want to talk about. Thank you very much. Yeah. We got enough questions. Great. Okay.
Maybe I'll ask one.
Yeah.
So on the other side of the pond, Seamus Davis is emphasizing the fact that you need to go beyond a 1-band Hubbard model, that the oxygen interaction with the d electrons is very important in quantitatively understanding the size of the super exchange, and it's really a charge transfer insulator. How does that come into your picture here? I don't think you're disagreeing with that, actually, so what about the debate of 2 bands or 3 bands versus 1 bands in this whole story?
I agree with you, and I have 2 things to say. Number one is related to your earlier question. I think this chemistry played the role why the electron doped and the hole doped, even though in spirit similar but quantitatively different. The second one, I think you should talk to Tom. They have made progresses. Actually, the 3-band was even better. Okay, and I always felt it's about 2 decades ago. I wrote this paper with Nagaosa to say that if you think about also the lattice degrees of freedom being relevant to the problem, then though P-type and N-type can be quite different, because you will be, one is much better coupled to the oxygen, the other will be really just going into copper. It's fairly natural to say this will be different of that. And so I would say, how to say it, if you want to go into more refined details, it's probably important. But on the other hand, I'm trying to address the chain of thought started with the seminal paper by Phil in the one-band Hubbard model. And within that framework, it appears that by adding this interaction, you actually can tip the balance. But you can take the problem to even higher level should we go beyond that framework.
Yeah, it's just
yeah. I talked to Tom. He says he said it's quite consistent with D-Wave, but I don't know the answer to your question. You need to talk to him. Yeah. But when I look at the picture, certainly in this archive, looks D-Wave to me. Arcadia, you want to ask a question?
Yeah, just comment the following years. There were also on elaborate calculations for single, double, triple chain by Giamarchi. I think they were both theoretical and numerical, analytic and numerical. And yeah, I don't know exactly what they say. I'm just commenting that.
I don't know.
Okay.
Yeah.
Well, so thank you again.
Okay, thank you very much.